you very much, Peter, and I thank very much the organizers for making this possible here and for giving me the opportunity to speak about research that is taking place in a larger framework, which I would like to call the Lorenzen project, in which which was, I think, I could say, ideated by Thierry Coquin, and into which also Henri Lombardi is participating. And in this project, there is a mathematical component, but there is also a historical component and a philosophical component, and I will speak today about the historical and philosophical component. As you see, I'm speaking freely without slides, and so if you would like to make me write down something, just tell me and I will write down some piece of information which you would like to see written down. But I prefer to speak freely without slides. So how to begin? So the first part of the talk will just be historical. I will just try to make a non-teleological historical account of Lorenzens contact with Gödel's incompleteness theorems. So Paul Lorenzen was trained as an algebraist. He was a student of Helmut Hasse and Wolfgang Krull. We already had the name of Wolfgang Krull in the last talk by Daniel Wessel, and it's exactly in this framework of making a theory of ideals that Lorenzen was working on. And in the context of the theory of ideals, he was confronted with this central question in commutative algebra, which is, when you have a certain number of elements, how can you introduce something which plays the role of the greatest common divisor, the GCD? And you can ask the question for a finite number of elements, but can also ask the question for an infinite number of elements. And Lorenzen, when he was confronted with this question, he had really the reaction, or he had the conviction that the right way to consider this is exactly in the Gentzen style, which means a GCD in commutative algebra is introduced by an introduction rule, and there is a corresponding elimination rule. And in doing this in algebra, when you have an infinite number of elements, then you write down something that is now known in proof theory as the omega rule. It is difficult for me to really decide whether Lorenzen had read Hilbert's 2 papers in which the omega rule first appeared. I don't know whether he just did it naturally because it was really the context of commutative algebra which enticed him to do so. But anyway, today one can say that if the omega rule plays a prominent role in proof theory, it is through Schütte's reception of Lorenzen's work. I'm just speaking, I'm about to speak. Because what happened afterwards is that Lorenzen understood that the consistency of arithmetic has an algebraic counterpart, or has a counterpart in lattice theory, which is just the construction of a free object. So exactly in the framework of Gentzen's first proof of consistency, to say that arithmetic is consistent is nothing but to say that a certain free object exists on the basis of a partially ordered set. And this free object, I will just say it now, I don't want to write down a definition because in some sense it's pointless. I also hope I can just say it. So it's the free, countably complete, ortho-complemented semi-lattice on a partially ordered set. And nothing more, nothing less. So you write down a certain number of rules, you prove that certain rules are admissible, and you have the free object at your hand. And so what I'm speaking about now happened in 1944, and in 1945, he wrote another version of the paper in which he did the same thing in a slightly, let's say, more readable form, and in which he constructs the free, countably complete Boolean algebra over a partially ordered set, exactly with the same ideas I was just speaking about. And in the introduction, he would say, all this happens in a finitary setting, exactly in the framework of Hilbertian ideas. He would say, I'm just working in the context of Hilbert's program. And so the first encounter with Gödel's incompleteness theorems happened in his correspondence with Paul Bernays. So contact was made with Paul Bernays through Heinrich Scholz in the years 1945, 1946. And it was Bernays who told him, well, you see, you can't pretend that this is finitary because there is Gödel's incompleteness theorem. You have to guide the reader somehow. You have to tell the reader where, in fact, what you're doing is not finitary, and where, in some sense, and how you escape the Gödel incompleteness theorem. And let's say more especially the second Gödel theorem, which is that the consistency of arithmetic is not provable in finitary means. And so in the end, Lorenzen would say this in his introduction and would say that, well, his proof is not finitary, but is still inside Hilbert's program. And I would say this first reception of Gödel's theorem really shows how much Lorenzen was somebody who was thinking, let's say, from the core in a constructive way, which means that for him, the omega rule is constructively acceptable without any kind of problem. For him, what we call finitary today, which means really to do some, to work with, I think in Schütte's and Lorenzen's terminology would say a fully formal system and Vollformalismus. I don't know exactly how the complete. This was not for him the right way to imagine to do mathematics. Mathematics happened for him with really a plane encounter with infinity. And for example, with the omega rule, or one has really an intuitive way of understanding that if we have a constructive way of knowing that something holds for every integer n, then you can deduce that it holds for all integers n. I think you understand exactly that there's a little difference between the first thing I said and the second, and I also don't want to lose time on this. But so to say, this first encounter just showed that Lorenzen did not really think that all these, that Gödel's incompleteness theorem were really relevant. But they became really relevant to Lorenzen's career slightly afterwards, and in the following way. So this, now I'm speaking of the year 1947. And in the year 1947, he wanted to do something which, in some sense, I would say, mathematicians still try to do today, and I would put also this workshop of this morning, type theory in type theory, inside this, this framework. He wanted to understand his own proof of consistency of arithmetic, and he would like to understand, which means to formalize, to see what kinds of what kind of logic is used in the proof of consistency, and so trying to tell the meta theory, to tell precisely the meta theory in which his own proof of consistency would have taken place. And so he did so. So there are manuscripts you can find in the Paul Bernals Nachlass in Zurich about these formalizations. And here, so his idea was exactly as one can see in, I would say, in many contexts, in also in today's logic. He would try to get rid of any kind of intuition, of kind of what we say, what one would call insights. Really try to see how one can tell everything in a strictly mechanical way. And here it was again the correspondence with Paul Bernals, which helped him out of this quest. It was Bernals who told him, well, you see, every time you are constructing something, every time you do some constructions, you need some insight to know that the construction you are doing really fulfills the requirements you want from it. You cannot remove any insight from mathematics. You cannot think that in the end mathematics would be a mechanical activity. And he would refer to Gödel's incompleteness theorem in this respect. And there Lorenzen really understood that Gödel's incompleteness theorem would be for him a wall, a barrier which he had to respect or which he had to break. So perhaps one could, or let's say, respect, break, or ignore. Let's continue the story to see exactly which kind of alternative Lorenzen took in the end in this respect. So what happened then is let's say is that really this what I'm speaking now is I think now I can say it's the most important event in Paul Lorenzen's life. It's on the 15th of October 1947. He called it afterwards der Zusammenbruch der Orthosprachen, der Zusammenbruch der Metatheorien. For him, it was really just a collapse of his scientific endeavor, and he knew that also mathematics are taking place in real life. And it's quite funny to talk after Daniel Wessel, who I would say found a very beautiful way to speak about this, also with this citation of Sarah Kaufmann. And so the thing that happened is that Lorenzen went back to his philosophical teachers, and his teacher of philosophy in Göttingen was Joseph König, one of the main exponents of the so-called Lebensphilosophie, philosophy of life of Wilhelm Dilthey. And I'll just say one citation of this philosophy of life. Hinter das Leben kann die Erkenntnis nicht zurückgehen. So knowledge cannot go behind or below life. Knowledge cannot precede life. Life precedes everything. It's about, I think this corresponds exactly to the way Daniel West was speaking about earth and sky. There is the earth below us, the earth is kind of bearing us, and the sky is above us. We have to start with the earth on which we have our both feet well grounded, and then we can build up everything. And as I say, this is really thanks to Gödel's incompleteness theorems that he went back to life, that he really tried to find a way to build up logic on some other fundament than formalizations. This is how he came to first to operative logic and then to dialogic logic, which were all just ways of finding, of seeing how logic is grounded into life, how logic is grounded into everyday experience, and how the logical constants are really just something that really from life helps us to construct knowledge. But it comes from life and goes to knowledge. It's not some axiomatic system. It's not some calculus that comes from the sky and it is cast upon us and to which we have just to conform in any way. And so just to finish with this historical part, so in this book Metamathematik by Paul Lorenzen, which was never translated into English, but which was translated into French and Spanish, there is a complete discussion of Gödel's incompleteness theorems. So I think it's a good source also to learn about Gödel's incompleteness theorems. And I want to finish with the last book Paul Lorenzen wrote, which is called Lehrbuch der konstruktiven Wissenschaftstheorie, which has not been translated at all. And what he says there is the following thing. Die Metamathematik wurde eigens dazu geschrieben, die Irrelevanz des Gödelschen Satzes für den methodischen Aufbau der Logik zu zeigen. So also in 1987, he said how much Gödel's incompleteness theorem was for him an obstacle with respect to which he had to find his way, and as you say, perhaps when you read this irrelevance, one whether would say it's something between to destroy the wall and to ignore the wall, to build logic just aside the wall, and to see that logic has a whole realm also aside this wall, and the wall would not just enclose logic, it would just be on the side of logic somewhere. Perhaps I should translate it to English. So in this book of 1987, Lorenzen says that, or did I say it in English perhaps already? I'm perhaps a little bit too nervous and I'll say it again anyway. He says that he wrote Metamathematik just for one reason, which is to show that Gödel's theorem is irrelevant for methodic construction of logic. So I have a few minutes left, and in these few minutes, I would now switch from this historical account to some more philosophical reflections. And so how can what more can I say than I already said? So there is one point I want to tell again, which is I think very important, which is really to see that I think everybody of us knows it, but here one can really see it very, very concretely, that constructive mathematics having really in an intimate way the omega rule at his disposition does not happen in a finitary framework. And this is already a reason why Gödel's incompleteness theorems do not apply exactly as is to constructive mathematics, and why one can really speak about the consistency of arithmetic as being constructively established without having to fear Gödel's incompleteness theorem. Another thing I would like to speak about here philosophically, and which is also very strong in Paul Lorenzen's work, is the way the position he takes with respect to axiomatic systems. So as we see, Gödel's theorem is a theorem about a certain axiomatic system. This axiomatic system has accidents in it. It is chosen in an accidental way. When one chooses axioms, one is in some sense behaving empirically and trying to choose the best fundament for a given science, and then to see how on this fundament of science one can build up things. And Gödel's theorem is then a theorem about any attempt to construct a fundament which contains contains arithmetic. But the thing that Lorenzen was really interested all his life was, and he liked to say it exactly in the following words, which are kind of strange, is how can one prove axioms? And it's exactly the same sentence that you can find in Clavius 400 years before, which means that in mathematics, for Lorenzen, as for Clavius, the real question is not to, when you're doing mathematics, is not to consider a given axiomatic system. It's really to reflect on axiomatic systems. And when you are reflecting on axiomatic systems, you have to think about the framework you're doing it. And this framework in which you are thinking about axiomatic systems is not meta-mathematics for Paul Lorenzen. It is mathematics itself. You have to really understand, you have to really be aware of the fact that when you're doing it, you can only rely on well, your personal and interpersonal conception of truth, of how you're building what we call in German Evidenz, but I'm not sure exactly how you say it in English. How you can really feel intimately and interpersonally the connection between hypothesis and conclusion, exactly in the sense of Husserl. And that in this way, constructive mathematics is really a non-axiomatic and a non-axiomatic way to do mathematics, a way to really construct mathematics out of nothing, really out of our very intimate understanding of what it means that we have at our disposal the infinity of natural numbers, which is just there, which we all share here, and for which any formalization just does not give justice. And this fact of not giving justice is just one instance of Gödel's incompleteness theorems. I'll just try to scan my brain to see whether I said every essential thing I wanted to say in this talk. And I think so, yes. I said everything essentially I wanted to say in this talk, so thank you very much.